Today we will see the chapter sets and relations. Okay. Okay. So before we go into sets and the relations, so let us define what we as a set. Okay. So now before we go into sets, when you are dealing in your real life or in a mathematics or any problem, you always have some group of objects and you have a name for it. Correct? Am I right? For example, you can say, okay, I will tell you. Let us take an example in a mathematics. What you do? Trigonometric functions. Okay. When I write trigonometric functions, is there only one function? There's a collection. What was that? It said sine. Let me not draw this bracket. What are the trigonometric functions? It be sine, cos, tan, sec, cosec, cot. Okay. Then I can call not just functions. I can say triangles. Triangle. When I say triangle, does it represent a single triangle? There can be different type. What? Acute triangle, obtuse triangle, right triangle, equilateral triangle, isosceles triangle, scalene triangle, or many triangles, right? So you can write it a symbol or write a name also. So what happened? What you see is actually forms a group. Am I right? Some group of functions, we call that as trigonometric functions. Some group of triangles, we call common number triangle, but they have other sets. So when we say triangle, it's a group. Group of objects. Correct? This is the objects. So I can say polygon. When I say polygon, polygon starts with what? Triangle. Am I right? When it has three sides, it makes what? Triangle. Am I right? And then when it is four sides, rectangle. Okay, not necessarily rectangle, it is quadrilateral. Quadrilateral is a polygon with a four sides. Then we have pentagon. And it goes on infinity, right? When it infinite sides, yes, correct. It goes up to circle, correct? So now this is also a collection of objects. We have a name polygon. Okay. And similarly, when I take a quadrilateral, you can have other names also. Yeah, quadrilateral. We have square, rhombus. That is square. Tell me square, rectangle, rhombus, then parallelogram, then trapezium, right? Not just this. Okay, we have other collections are basically collections, right? So we have other collections also. Say for example, the alphabets in your name. Okay, what in your name will be? In your name. Your name. What was that? A L V I N. Okay, my name. S U N D E R. Okay, so means we have a collection. Okay, we have collection of many objects. The collection of objects. Okay, so now I can have still more also. Something like that. Beautiful girls in the class. In my class. Why beautiful girls? Beautiful boys in my class. Lazy people in an office. Okay. Costliest watch. These are also group, right? We have a group of people. Am I right? So group of boys, beautiful girls, group of beautiful boys. So when we are doing this mathematics for this collection of objects, okay, and then when you are to do the mathematics of the collection of objects, that's what you call as your sets and relations. Okay. Now when you want to do the mathematics of this collection of objects, mathematics needs well-defined object. Okay. So what happened? It should be well defined. Okay. Among this group, I said, is there everything is well defined? Which are not well defined? Name is there any? It's not well defined. The name spelling is not well defined. Can you tell me whether the beautiful girls in the class is it well defined object?
No.
Okay, because some girl will look beautiful for me, but not for everyone. Okay, for someone, some will be beautiful. You can't categorize. Okay, so for beautiful boys again. Okay, some boys will be looking very beautiful for many girls, but certain girls will think this is a horrible boy. Okay, lazy people. How do you define? Costliest watch. Some watch may be costlier for you, but for someone it will be cheaper. For someone it can't be affordable at all. So these are all there for these things. They are not well defined. Well defined objects. Okay. Whereas here, when I say triangle is a well defined object. A polygon with 3 sides is a triangle. Okay. And now, depending upon the angle of the triangle, I had defined the object. It's a well defined object. Okay. Then your name. Okay, your name, letter alphabets, quadrilateral, the polygon, trigonometric functions, natural numbers, whole numbers, real numbers. Okay, though the numbers goes to infinity, but they are well defined. 1 will be 1 for you, for me, for everyone. Okay, 5 will be 5 for you, for me and for everyone. The number of digits on a die. When you roll a die, how many digits you get? 6. 1, 2, 3, 4, 5, 6. This is going to be same for everyone. These objects, they call the number, these are well defined. Okay, there is no ambiguity in it for everyone. Okay, unless for these reasons, here we have ambiguity. We don't know that. They are not well defined. So set is nothing but a collection of well defined objects. You got it? This is called as your set. So the set is what? What we call as set. It is a collection of well defined objects. This is called as your set. Okay, so because to do mathematics, you need the object to be well defined. Then only you can do the mathematics. Okay, you can't say good people, bad people. Mathematics is not psychology. Okay, so you can't say that good people, bad people. Okay, so you have to define. A good means for everyone it should be same. So that's what the group of and okay, this is what we call as your set. What is that? This is the set. Set is a collection of well-defined objects, and the object which forms a set for here SUNDER. ALVAN, square, rectangle, rhombus, parallelogram, trapezium. These objects are called as elements. Okay, individual objects which forms the set is called as your elements of the set. Okay, and there's other name also, they are a member. They call elements or a member. Okay, and there's a symbol. Suppose, for example, suppose you have okay, and okay, they given the name also, na? Yeah, right. So what do they use? Generally, what happen? Then you have a name, right? For every collection of well-defined objects, you are given a name. Your name, my name, quadrilateral, polygon, triangle, trigonometric functions. So when you want to write a set, this group of sets, this group, okay, I have to give a name. Mathematics, you have to give a name. Am I right? So I will call this as probably something like A. For this group, I will have something like B. So again, okay, so when what we do is we represent capital letters, capital alphabets for representing a set, and small alphabet for representing the elements. Okay, so something like when we will see. Okay, so I will see what do you mean by that. Okay, so I will show what means. I want to represent this each element. In mathematics, I have to assign I'll assign some symbol to it, right? So let me call this as X. Okay, so each element, when I represent a symbol to each element, here also I can have this as A, B, C, or X, Y, Z. I can define I can give a name to the each objects. Okay, so that symbol you represent it by small alphabets. Okay, so here what happened? So then if I call, so here this is X, then if I call, if X is sine theta, if a sine function is called as X, and the set of the trigonometric functions call it as A, then I can say X is an element of A. Correct? Because sine X, because X is nothing but sine function. Now it's not, but X is element of A. So the symbol is what? X is an element of A. You got it? So that's the way you have to represent. You have to represent the way the mathematics is a notation. It's just for convenience. Okay, we represent the set as a capital alphabet and the individual element as a small alphabet. Okay, you can't. So because you have to follow a proper procedure to do. Then only others can, to everyone to understand it. Okay, so this for you know that natural numbers, real numbers you write it is R. I think whole number W, natural number Z. But natural number is something you write N also. I don't know. Here they written as N only. Yeah, correct. What is Z they written? Z is usually for complex numbers. N. I think whole numbers they are using it as Z. I think so. Integers. Are they integers? They are writing it as Z. Okay. So, but anyway, fine. So this is all the. For example, integers. Integers is a set or not? Correct. Though it is an infinity, it is a set. It is a well-defined numbers, well-defined objects. Okay, so that's what you call as your set. Okay, so now when we have, so now what the whole idea is we want to do the mathematics of this collection of objects which we tag it as, which we name it as set. So then how am I going to represent that collection? You got it? See, if I want to represent, I want to somewhat write it down. I want to represent this is a set. Okay, you can do it in any form. So typically there are three forms are being used. Okay, so because you are saying, see, this alphabet A, L, V, I, N, this is a collection. I have to put a symbol, this is a set. And this is a set which is derived from the English alphabets. Okay, so if I call the English alphabets, as some set, okay, then A, your name, okay, that subset will come. This is all an element of that English alphabets. Okay, subset will come later on. I will tell you. Fine. So this is what. And now, what I say, I have to represent this collection, some symbol, some representation, some symbolic form. So there we have three types of representation of sets. Okay, so we will see that. So now, so we have defined what do we mean by a set. Set is what? A collection of well-defined objects is what we call as a set. Now we have to see how we are going to represent a set. Typically, the sets is represented in three types, three forms. Okay, in three forms people represent the set. Why do you need three forms? According to the convenience. Okay, because certain form will be convenient, is easy to express in certain form. Sometimes it is easy to express in some other form. So that's why people represent the sets in different forms. Okay, so what are the forms is, first form is what you call as a roster method or whatever, roster method, okay, what they say, either roster, tabular or list, all are same. Okay, and what is this? This is just represent the objects, all the possible objects in a curly bracket. Okay, when you represent, all the elements, if you represent all the elements of a set in a curly bracket, then you call that method as your roster, tabular method. This is the simplest form. Suppose your name, the alphabets in your name. So then what happens? I am going to have, let me name the set as A. So now A is a set which contains the alphabet in your name. Okay, so what is that? A, L, V, I, N. So now I have another alphabet, another set, B. B is a set which contains the alphabets in your surname. So what is that? Sahayanathan. S, A, H, A already written. You don't have to repeat again. S, A, H, A, then Y, A, N, T, H is there already, A is there, N is there, that's it. You got it? So you don't repeat the same letter again and again. Okay, I can have another one also. The numbers on a die. 1, 2, 3, 4, 5, 6. Okay, you can have many things like that. Okay, numbers on a die. Sides of a coin. Head and tail. Okay, so these are all, this is the way. What I am doing, I am taking the collection of objects and just write the elements as it is. All the elements I put it to the comma and close them with a curly bracket. So this is a simpler form. This is what you call it as your roster or tabular or list method of representing a set. Okay, this is simple, but usually this is not the, because many times, okay, you can have one more thing also. Na? So for example, if you have E, if it is a natural numbers, so tell me what will be? 1, 2, 3, 4, 5, dot. If it's an infinite, you can put is 2 dots. That's is continuous. Okay. So this is the way you can represent the set in a simpler form. So roster form or tabular list form. Okay. So the next method, the next type is what? The next one is what you call as a set builder or your rule method. Means you, okay, I'll explain you. That is what set builder method. Or otherwise called as a rule. Because you define a rule. Okay, so let us write. For example, let us go to the same one, what you have done. First one. We had the A. What was A? A is a alphabets in your name. Okay. So what do you say? A, L, V, I, N. Okay. In a set builder form, if you want to represent this symbol, what I write, A is X such that X is the alphabet in name. You got it? Die. Okay, what is the alphabet? What is the die? B. What we had? 1, 2, 3, 4, 5, 6. So you can have what happens. So in a set builder form, you write it as X such X. You can say X such that or X is an. They're simple. They have what the name usually call it such that. But here they write it as in. Well, they have not mentioned anything in your book. Anyway, forget it. Such that we call. Okay. X. B is a set of X such that the X is the numbers on a die. Okay. You can have. Okay. Another one we did, right? C. What was that? 1, 2, 3, 4. Right. If you want to write this in a set builder form, what do you write? C is equal to X.
Such that X is the numbers.
Natural numbers. Correct? So basically, x is an element of natural numbers. It's not necessary you have to write it in this form. If you have this one, you know, because natural numbers. These are basically natural numbers. X, such an x element of natural numbers. Okay. Okay, and then otherwise you can have something like, yeah, this is another one example what they given in a book is say something like D is equal to, say for example, 1, 4, 9, what is it? You tell me, what is the next one?
Okay, square number.
Correct. So then what happens? So in a set builder form, how will you write? X such that x is an element of, first of all, this is a natural number and x is a square. Correct? And x is a square. Okay, so this is the way you have to represent, and this way something they given na. Days. Okay, that's also good point. I forgot that one. Days of a week: Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, and Sunday. Correct? Okay. So if you want to write a set builder form, tell me.
X is that X is the number of days in a week.
Days of the week. Number of days is just 7.
Okay.
Days of the week. Okay, you have to write the proper way. Okay. X is the days of the week. So here you have to give the proper. Is the number of days in the week then becomes wrong. Number of days is what? 7. What here is what is written is the days of the week. You write days of the week. Okay. So this is how you can represent in the set builder or rule form. And the third representation, it's basically a pictorial or pictorial representation of set. Okay. And that is often very useful to very useful sometimes to have a to have an idea by looking into it. You don't have to really think about it. Just you have to pictorially represent the set, and then you can do all the relations between the pictorial representation, mapping, and you'll study later on. So there you can see it very easily how you are going to map all those things. Okay, so that representation is called as your Venn diagram. What is that? Venn diagram. Venn diagram is nothing. See, there's nothing like that. You have a collection of objects, right? You put the objects in form of a curly bracket. Okay, because that's your curly bracket or something. There's nothing like that. I can make a box and put all the objects into it. And then I call that as a set. Correct? So that's what you call in a Venn diagram. What you do, you put up all the elements. So for example, the number of days in a week, right? Let me call that A. Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, and Sunday. I want to represent this in the Venn diagram. How many days? 7 days. I'll put 7 points. 2, 3, 4, 5, 6, 7. Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, Sunday. So this is what you called as your Venn diagram. You will see when I put the elements into the box. Now why do you need the box to be a square? I don't like a square. I don't want the box to be a square. You can put it in a triangle. It's also allowed. Why a triangle? You draw it in a circle. Okay. I draw it in a circle. That's also allowed. Why I want to draw it a circle? I can write it as a elongated circle. Oval kind of. I will not write like this. I will write like this. I'm going to write it like this: Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, Sunday. And then this is how I want to represent. In that case, what happened? You don't put a circle, you put a elongated oval symbol, whatever, into it. Okay. So this is the way, this what, when you represent this way, that's called as a Venn diagram. Okay. So we have defined a set.
Then what about infinite numbers, like natural numbers?
We will come. In Venn diagram, when you want to define infinite numbers, you will see. You can't represent there. Okay, you can represent the Venn diagram. This means you will put dot, 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 and dot. So that's how the other forms will come into easier. Okay, you can't do the Venn diagram. You get infinite numbers, you can't do. Okay, there's a way you represent. You don't, then that case, don't put it as a point. You put a circle and call it as a n. That means n is completely a natural numbers or something like that. Okay? Okay, so that way you can represent. These are the three representations of a set. Now, so we have defined a representation of a set. So now, then we can define the types of set. What are the types of set we have? Okay, so let us see that. Before going to the types of set, there's another one term also, another one quantity is also important. The number of elements in the set. Okay, suppose you have a set. Okay, say as I said, what I can say, for example, let us take your name, surname. What happened? Let me call that as your A. What are elements we got? S, A, H, Y, N, T. That's it, right? How many?
5.
6. Okay, so then if you want to represent how many number of elements in a set, that I represent it as n of A equal to 6. Correct? Suppose if I write my B is sides of a coin, n of B will be equal to 2. Okay. Okay. Now I have another one I will write. Tell me. So for example, I am writing in a set builder form. C is equal to I will write it as C as X, such X is an element of natural numbers and minus X is equal to X. Do you have a number?
No.
Is there anything there?
No.
No. So in that case, what will be n of C?
0.
N of C will be 0. Okay, you got it? So this is, and then from here, so then now you can see the numbers are differing. When we can define a set, you have defined a set, but that set, actually when you see, that set contain nothing. Right? So when I put a number of set, you find that nothing will come out. So then this type of set, where the number of elements in the set becomes 0, but no, is that then you call this as your empty set. Means what? It doesn't have any element. Okay, so the symbol is what? Usually empty set is represented as just like this or a symbol 5. Okay, so this is the first one. What we have is a empty set. So what is n of empty set? Will be 0 always. Okay. The next one is singleton set. So this is what? N of this will be as an empty set, right? Empty set, what the symbol we had? Something like this and for 5. Okay. So there. Singleton set. By the name itself, you can tell. What is that? only one element, not digit. It's only one element. Okay, here we don't see good digits, the object, elements. Okay, so can you tell me example of a singleton set?
Mm.
Ah.
You can put x is equals to negative x in whole numbers.
Correct. A is equal to x such that x is an element of whole number and
X minus x
is equal to x. So this is what singleton set, because when it's a whole number, of course you have 0. Am I right? So this is nothing but 0. Okay, this is only one element. So this type of set is called as your singleton set. Okay, and the next one is your finite set. Yeah. Now you know what. So what will be n of a? Tell me.
N of a equal to 1.
Equal to 1. Okay. So can you know what is a finite set? Next one is finite set.
Finite number.
Finite number. That's it. Okay. Is 0 a finite number?
Yes.
1 finite number?
Yes.
So in a finite set means even your empty set and singleton set is also a finite set. Okay. So the point is, finite set, what happens? You have a n. Okay. So in a finite set, what happens? You have the n of that set should be a finite number. It should not be infinite. When I say when I form a set of natural numbers, is it a finite set?
No.
Because it's the infinite numbers I have. Correct. So in a finite set, what happens? N of a should be finite. Okay. Can you tell me if A is English alphabets? X, where X is the alphabet in English language. Is it a finite set?
Yes.
Of course, it's a finite set because the n is going to be not infinite. Okay. The numbers on a die, these are all finite sets. Okay. So this is what a finite set. So once if I define finite set, can you tell me what will be the next set I can define? Infinite set. Okay. Because if the number elements are infinite, then I call that as a infinite set. Can you give an example? The art of example. Set of natural numbers. Whole numbers, real numbers. Okay. Points on a circle. Points on a line.
Sides of a circle.
Okay. The lines, the number of lines that can be passed through a point. Infinite. Okay.
Meeting.
Correct. Intersecting. The slopes of a line, intersecting lines. They can be infinite. Okay. So these are all what you call as your infinite set. Okay. And the best thing is number of points on a circle. All those things will be the this one. And then comes the important thing. Something what we call as. So now we have defined the sets: empty set, singleton set, finite set, and infinite set. Now we are going to something called as subset. What is that? I would say before going to subset, I think let me go with equal set. Okay, what is that we call equal sets? EQ. Can you tell me what is equal sets means?
Two sets have equal number of elements.
Equal number of elements? No. Same elements. Okay. I'm giving you okay, let me give a nice example for that. Okay, I'm going to give a x such that x is the alphabet in name. So let us write it. Name Mary. Okay. I'm giving another set. B. X such that x is the alphabet in name Ramya.
Ramy.
Okay, so tell me, if I want to write it in the roster form, this will be what? A will be what? M, comma, A, comma, R, comma, Y. And for B, R, comma, A, comma, M, comma, Y. Are they both equal? They equal. Okay. In a set representation, it doesn't matter how we are going to, in what sequence we are writing the number. It doesn't matter for it. Okay. So these two sets, even though I have represent these two sets are different, but when I go into sets, they both are same. So these sets are called as your equal sets. Okay. And there can be one more thing. Then I can say, then come to what you said just now. This is what? For the sixth one. Then I have equivalent sets.
Equal number of.
Yes. Simple. Are this A and B equivalent?
No.
Why not?
A is twice. A comes twice.
No. When you write in the set, you don't write it twice. Or when you say equivalent, if two sets A and B are equivalent, if n of A is equal to n of B, are they equal?
In that, no, they are not equal.
This is a set.
Okay, that's a.
Of course, here also it is same.
No, the number of. That's in the first one.
X is the alphabet in the name Ramya.
The first one, Mary, it's four elements.
Correct.
And the Ramya, it's 5 elements.
Where? A is twice. You are not supposed to count the same alphabet again and again. Okay, I can't write it one more A. I told you. The A is an object in this name. That's it. A can appear many times. Doesn't matter. Okay, so A is an object in this one. Got it, na? So now, are they both equivalent?
Yes.
They are equal. All equal sets will be equivalent sets also. Of course, the numbers is going to be same. Okay, so now you say other one. Now I call C is X such that, okay, let me call C is X. X is the numbers on a die.
Okay.
What will be N of C?
6.
N of C is 6, correct? So, is C and A equivalent?
No.
Yeah. Okay, because that is N of A is, this is 4, this is 6. So, we have defined, so equivalent sets. Equivalent sets will have the number of elements, as N of A or N of B should be equal. Whereas, in a equal sets, each element should be equal. Every element should be present on the set. So how to define is every element of B is also an element of A, and every element of A is also an element of B. Okay. Now you can say it will be always. Huh? Correct? Sure? I am giving you the example. Okay, fine. Let us see. Is it always true? Okay, so let us take the first one is, okay, let us take the first one is Mary. Okay, so what is that? A is equal to same one. A equal to X such that X is the alphabet in name Mary. Okay. And now I am going to give B is again X. X is the alphabet in name Ramayan. Okay. So now you tell me in roster form, how will you write this one? M A R Y. The B will be R A M yn. Are they both equal?
No.
No. Why? All the elements of A are the elements of B, but all the elements of B are not the elements of A. Okay, so in equal set, we should mention all the elements of A are also the elements of B, and all the elements of B are also the element of A. Okay, so once you define that, then you can see. So basically, you can see this set A. So you can, all the elements of A are in the element B, but the reverse is not true. That means, so you can actually, you can form the set A from this set itself. Pick up the elements and you can form the set. Am I right? That's what we have done. So then I will call A as a subset of B. Because basically A is formed by picking the elements from the B. It may not be all the elements, right? And the symbol, how do we write it is, how do we write the symbol is, so then we will call here A is a subset of B for this problem. Now can you tell me here whether A is a subset of B here?
Yes.
Here it's yes, they are equal. So there what happened? A is a subset of B. And can you say B is also a subset of A?
Yeah.
Correct? So in that case what happened? So you can write this as, when it becomes equal, so you write it as this symbol like that. Okay, so this is how we write. And okay, now can you tell me, is B a subset of A here? So then how do you write? B is not a subset of A. This is how you represent the sets. Okay. Okay, I made a mistake. Okay, when it is a subset, the symbol of subset is this. General symbol of subset is this. Okay, so that's something called as a proper set. We will come there. Okay, so general symbol is this. Okay, what I written here is proper set, that we'll see later. And now there's one important point what you want to say is general symbol of subset is this. Okay, so all subset you have to write it like this. When you put only this one, that's what you call as a proper subset. That I will come there. Fine. And now tell me this empty set. Can empty set be a subset of any set?
Yes.
Of course, right? So empty set is a subset of all sets. Okay. And can any set be a subset of itself?
Yes.
Of course. Correct. So that's what. So these are the points what they have written there. Okay. Every set is a subset to itself. Okay. And there comes your next point is your, that's what comes here. Superset. Okay. So, yeah, from the name itself you can say. What should be, so here, let us take for this portion. So what we said, A is a subset of B. Am I right? Now, can you tell me what is superset? Reverse of that. B will be the superset of A because all the elements of A are there in B already. Okay, so that's what you call as a superset. Just reverse the symbol. So what happens? So B is a superset of A. Okay, so that's all you have to do it. You understood now all these things, eh? Yeah, then comes the proper subset. That's what's important is because I made a mistake. I wrote a symbol for proper subset. Yeah, correct. So what we are going to have, let me write down this one. So this is, I lost the number. One is what? This is the equal sets, equivalent sets. And then we had a subset. Okay, so what we had? 7. 7 was what? Subset. And 8 is superset. And let us come for the 9. Okay, what you call as a proper set. We can take the same example, proper set. Okay, proper set is what? So this, proper subset. Sorry, what the name is? Proper subset. So the proper subset is proper subset means, see, for example, here let us take A is a subset of B. That means what? All elements of A are the elements of B. So then we call it subset. Okay. Now there should be at least one element in B which is not an element of A. Okay. So then you call this combination A and B. A is the proper subset of B. You understand? So that you write it as A is a proper subset of B. Because all elements of B are not in A. At least one. Okay. And you should never use an empty set. Empty set is not a proper set. Okay. So A is a non-empty set. Okay. A non-empty set where every element of A is an element of B. Whereas there's at least one element of B which is not an element of A. That you call as your proper subset. You got it? So these are the proper subset, and then you have power set. Yeah, power set is also interesting. Okay, the power set. Let me remove this one. This all will see when you are trying to do these relations and all. You have to know this definition, these types of sets. Okay, then you can. The next one is a power set. That's what then we will write it as. So, given a set, try to write down all possible subsets of the set. And that whole combination of subsets is called as a power set. Okay, let us take for example, tossing a coin. So, what are the things you will get? Head and tail. Okay, so let me write your set A as head or tail. What are the subsets you can form from this A? First one is empty set. That's also a subset. And then H, then T. That's it. What about this? I'm not telling it's proper subset. All possible subsets. Okay, and this is called as your power set. You got it? Huh? So you can keep on doing like that. Okay, so the symbol what they have written is, so for example, this is what P of A. Okay, so yeah, this is either they write it as phi also. Okay, these are power sets. We saw the power sets and equal sets, and the last one what you're going to see, that's the 11th one. That is an important set, what we call that is a universal set. Okay. So universal set is an important concept. Why it's an important concept? When you are going to do with this set problem something, you have to say the universal set means the whole elements of the objects what you are going to deal in that subject problem, they all belong to a certain universal set. If you are dealing with a, okay, let me put a very nice example. So you are dealing with a rolling a die. The numbers you are getting. How many numbers you will get? 6. Okay. And there I can say the universal set, if I say the integers. Integers are what? The universal set. Because the die is, all the die numbers going to be within the integers. Suppose I am going to different problem. I am rolling 10 dice or 20 dice. What is the total sum of the numbers you are going to get? Okay. So then, and this is the problem I am going to deal with. Now, can you think of what can be the universal set?
Okay. It'll be fine. Finite, right?
It will be, no, it can be finite, but I am saying is the universal set is the whole problem what you are going to deal, all the numbers should be there. Okay, and the whole thing, and you are not when you are doing the whole thing, you are not going to go out of that set. Okay, so now what I am saying, I am taking 2 dice. I am rolling 2 dice. I am asking what will be the what all the total number you get by rolling the 2 dice. Okay, or I'm going 3 dice. So all the numbers you get. Can you think of what can be that universal set? Which from where all these numbers should be there. Integers. Will it be a real number?
No.
Will it be a fraction?
No.
Integers. Correct? So the universal set here is an integer because you are going to do only the dice. You roll 100 dice. Still the numbers, total sum of numbers is going to be integers only. You got it? Okay, so that's what. So that's what you call as a universal set. Okay. So you are, okay, let me try it out. I'm going to find all alphabets from the boy's name. Can you think of a universal set?
Alphabets in English language.
That's it, alphabets in English language. Of course, I'm in an English name. I'm going to find out all possible alphabets from the English boy's name. And therefore, the universal set has to be alphabets. English alphabets. Okay, so this is how the concept of your universal set. So all sets will be a subset of the universal set. You got it? Huh? So that's what. Okay. See, the set of natural numbers n, the set of integers z, or the subsets of real numbers r. They all are natural numbers and integers are basically a subset of the real numbers. Therefore, real numbers can be seen as an universal set. Okay, because that contain all the numbers. Okay, so this is how, yeah, what is the symbol for universal set is, usually the symbol is U. Okay, so you understood all the thing? So these are the types of sets so what we saw today, we defined what are the sets, and we have defined representation of sets and the types of sets. Okay, tomorrow we will see something about operations on sets, how we are going to do the operations. Okay, that will be interesting. We'll find out the union, intersection, all those things we'll find out. That we will see tomorrow. Okay.